Let's try to decode and help you understand pages 11 through 16 in Chemistry 1124. It's talking about trends on the periodic table. And some of these terms they define but are still, you wonder what are they saying and why is it that way? It does not make sense, okay? So this first chart here on page 12 shows atomic radii. Now you know that radii is plural for radius, and that would be from the center of the atom to the outer edge. But basically, we're just talking about the size of the atom. So the bigger the atom, okay? So what are some things that cause an atom to be bigger? Well, one would be adding more layers, right? More energy levels. So that one makes sense. As you're going down the periodic table from top to bottom, each element going down is bigger than the one above it because there's another energy level being added to it. But here's a good question. Why, as we go across, do they say the atoms are getting smaller? That seems a little, you're adding more electrons, right? So you'd think, duh, it should be getting bigger, there's more electrons. So the best way I can explain this is, yes, you're gaining electrons as you go across, but we're also gaining protons in the middle. And so all these protons densely compacted in the middle act as a magnet attracting the electrons. So the more concentrated, the more protons you have, the more concentrated they are in the nucleus, the stronger their magnetic pull on those electrons that are whirling around. And so they're pulling them in tighter. Their orbit is tighter and tighter around the nucleus. So they're closer to the nucleus. So for instance, down here, potassium, K versus bromine. Potassium has some electrons in the outer shell, okay, whirling around, but there's not as many protons in the middle, so they are further away from the nucleus than over here when you get over to bromine, okay? So the more protons, they're pulling in on those electrons in the outer shell and keeping them closer to the nucleus. All right, so that's atomic radii. They have a little chart here at the bottom that shows it increases as you go down, decreases as you go across. Hopefully that helps you understand why. Now let's talk about this ionization energy. Every atom has one electron in the outer shell that it could be taken away from it in a chemical reaction. So let's think about trying to take away one electron from the outer shell and think about how strongly does that atom want to hold on to that outer electron, or does it just want to let go and say, I don't care about that electron, you can have it. You want it, you can have it. Because actually, if I get rid of that one electron, I have a full shell of electrons underneath and I have my full octet, remember that, the full octet? And so I am happy. So that's what we see here actually. These elements over here on the far left, they have a lower number, like around 400, some of them even 376. Is that the lowest? I think so. And so 400, 500, 600, they're kind of small numbers, which means they are more willing to just say, hey, if you want that electron, you can have it. I'm not going to hold on to it very strongly. Compared to electrons over here. So on this side of the chart, we have 1,300, fluorine 1,600, woohoo! Helium does not want to give up any electrons, okay? It holds on to its two very strongly. So that's just a relative way these numbers express how strongly they want to hold on to. The higher the number, the stronger they're holding on. The lower the number, the more willing they are to just let that go. Okay, so that's ionization energy. And if we turn the page, I think it shows a chart that there are trends. All right, so it increases as you go across, decreases as you go down. All right. Then we have electron affinity. So to me, these all sound very similar and get a little bit confusing. But I'm trying to simplify. I read through this several times. I tried to come up with very simple language. I'd suggest you write this down. And then as you read it, okay, think about my definition. So electron affinity is how much energy is gained. That'd be a plus number. Some of these numbers on this chart are pluses, some are minuses. Okay. Or lost. Lost means it's giving off energy. If it gains energy, that's called endothermic. Energy lost is called exothermic. Now we're going to learn as we move further into chemistry that in nature, reactions are much more likely to take place if energy is given off. Okay, it takes more, it runs against the second law of thermodynamics to add energy. Okay, so things tend to deteriorate and things tend to give off energy. So actually a negative number is probably more, shall we say, desirable, more likely to happen in nature. So an exothermic is more likely to happen. If it's positive, it actually means that that element really did not want to have an extra electron forced on it. It was not happy about that, and it said the only way you are going to make an electron attached to me is you've got to give me a lot of energy before I will take that electron, okay? So, however the reaction takes place, energy has to be added to that atom to force it to take an electron. Whereas a higher negative number, it's saying, oh yeah, I would love to have another electron. Give me more, you know? And it easily gives up energy in order to gain that electron. So look at the chart here. Some of the higher numbers are over here on the upper right-hand corner. And sure enough, fluorine already has 7 electrons in its outer shell. It only needs 1 more. Remember, 8's the magic number. So fluorine is just saying, give me 1. I just want 1. Give me 1 electron. I would love to have 1 more electron. I will be happy. High negative number, okay? Negative 322. I think that's probably the highest on the, almost the highest on the chart. Bromine's negative 325. Ooh, chlorine, negative 349. So those elements up there are saying, please, I want 1 more, just 1 more. The positive ones are this second family. Look, all those positive numbers, because they have 2 electrons, and they're satisfied. If you try to shove 1 more on them, they're like, I don't want that, okay? And all right, that's electron affinities. They talk a little bit about some of the general trends. And I don't think you need, I mean, you can read this. Don't get too hung up on all the numbers. Same with this chart down here. It's like too much information, okay? Don't get hung up on it. And then the last thing I want to point out is electronegativity, and that's down here in the bottom of page 16. That's how strongly an element wants to attract more electrons. Okay, so this electron affinity is an actual number of 1 atom, okay? Whereas this is a relative, it's almost like a magnet, measuring how strong is this magnet in wanting to gain electrons. So this is similar to what we just saw in the previous chart, is that the fluorine is the strongest, 3.98. It strongly wants to attract other electrons. So that's pretty close to a 4, and there's nothing bigger than 3.98 on this whole chart, okay? And then the smallest ones are down here in the lower left-hand corner. Those small numbers, francium, 0.7. That means it's not too willing to gain electrons. And if anything, is willing to give up electrons. But we're talking about how strongly does it want to attract more electrons. So in this corner down here, not too willing to attract, and small numbers, decimal numbers, they get bigger and bigger and bigger until you get all the way up here. We're going to find later this can be used to determine if there's elements that are in the same reaction and an electron is available, becomes available, which element is more likely to win the battle, okay? It's almost like measuring who has the greater strength. The bully, who's gonna bully out the other element and say, no, that electron is mine, I'm stronger than you are. Well, if fluorine is part of the reaction, is probably going to win every time. Okay, that's the world champion wrestler. He's got the most strength to take electrons away. But let's say fluorine's not in there and we have phosphorus and chlorine. Well, looks like chlorine's got a bigger number, so chlorine's going to beat out. Okay, we'll talk about that later. I'm just helping you see that's what these numbers can be used for later in determining how reactions proceed. All right, we'll stop there with this lesson, and hopefully that answers enough questions that you can at least answer the questions as you work through the pages in your workbook.